Welcome to 3Mac. Do you want to learn about computational design, advanced manufacturing, materials modeling, or integrity assessment? Then this is the channel for you. I regularly upload new content, so please hit the subscribe button below for regular updates. Hi, welcome to today's video. In this video, I will show you how to perform FE analysis on self-healing sheet memory alloy composite. This is taken from a request from a subscriber, so everything is from a research paper which was sent to me by the subscriber. The problem is not that complicated, but it requires steps to learn how to perform such an analysis, so I will go step by step, and in today's video I will just do one part of the simulation and we will cover the rest of the stuff later on. Okay, so what the problem is, we have a matrix and we have sheet memory alloy fibers into it, as you see here, and it can have a pre-notched sample or it can have a crack already inside the sample. So this is the initial configuration. Then in the experiment, what they do, they pull the sample in one direction and you see the crack starts to propagate, while your sheet memory alloy wires or fibers, they start to deform. And if you know the theory of sheet memory alloys can have elastic deformation in the austenitic phase, and then they start to transform into martensitic phase, and then they completely become martensite, and then everything is governed by that. Now if you unload the sample again, which is already transformed, then it again retransforms back to the austenitic phase. So this is martensitic phase, this area, and this is in between, and this is complete transformation back to austenitic phase, and same happens in the compression side as well. So how this is also termed as pseudoelastic response, shape memory effect, many terms are there, and that's why these called shape memory alloys. We worked on this for a long time ago, I would say almost 10 years ago, so my knowledge might not be that updated at this point from the research perspective, but what we did in that case was we expanded the shape memory effect, which is the pseudoelastic effect, to the elastic plastic part as well, because after a certain amount of deformation, with all the transformation has occurred, you will have plastic deformation in this material followed by failure due to the void growth, nucleation and growth. So that's what we did in our paper, and I will give you the reference at the end once I finish everything. So this is the problem here. We see we have two problems. We have a matrix which is an elastic plastic material, while we have shape memory alloy which has pseudoelastic response as shown here, and we need to define all these properties in the ABAQUS FEA software, and we need to see if we can simulate this crack behavior. So the problem is complicated, but it can be solved easily. We need to model these fibers, so we need to have like around 5 fibers in the matrix. We need to have a notched sample with elastic plastic properties, and then we have to define the crack propagation criteria along this line as shown here, because they found out that crack propagates in this direction. In the paper, when they simulated, they've used node release technique, so they already had nodes bonded here, and then as soon as you reach to the maximum stress, they start to release the nodes, and you will see this kind of crack propagation. So that's what they did, because at that time ABAQUS did not have that kind of robust way of propagating the cracks, or not, that was not common, I would say. So what else you can do is, other than using node release technique, you can use cohesive model here, because you know the direction of the crack, so you can use cohesive model and you can define those. Or nowadays people use XFEM, which is pretty robust in ABAQUS nowadays, so you can try that as well. In today's video, what I'm going to do, I will start, since you are learning these things, so as a learning point would be to do everything in the steps, and I have explained everything and it looks easy, but as they say, easy said than done. So that's the problem here. We need to do it and show that okay, it's gonna work. So what I will do is, I'm gonna first show you how to model this fiber using this pseudoelastic response in ABAQUS in today's video. In the next video, I will show you how to model the fracture if you have only matrix, and in the third video I will just integrate these two components together and do the actual simulation, but again using some fictitious set of parameters, and I don't want to really give you the whole solution. So let's move to ABAQUS and see how we can do the pseudoelastic response simulation in ABAQUS for a shape memory alloy only. Okay, let's jump into the details of how to model this. So I have already created a model. So what I did was, to model the fiber, I have just created this single line, how you can do it is go to the create part option, select 2D deformable and then wire. Then you can select a cable. In that case I think it was 6 millimeters long, so I'm just modeling that, and you see this is my length of that fiber. I'm calling it cable, sorry, but it's fiber. And then you go to the properties and then you define the material properties. So for the case of shape memory alloys, I have to define the elastic properties. These are again given in that paper for austenitic phase, which is the initial phase, and then for superelastic or pseudoelastic response, these are the parameters you have to define. Again, if you are confused about that, always good to look at ABAQUS documentation. Let's see if I can find something there. So this is there. I'll just go there and I will look at the keywords here, this one, and you see everything is defined here. M is the first term is the Young's modulus for the martensitic phase, then the Poisson's ratio of martensitic phase. So these are all here, which are these parameters here. Martensitic phase, Young's modulus, Poisson's ratio, then transformation strain was the similar thing as, if you remember, in the PowerPoint which I showed you, it was a total strain for the transformation. So that's also given there, and you can read it from stress strain data, which was again given in the thing. Then you have stress at the transformation begins, then stress at which the transformation ends. These are those values. And again, I think you can, if you go back, you can really link everything with that. So you see this is the curve I use here. So you see these are the start and end points for loading and unloading case, and then this is the total strain of transformation, and then this is under the compression side. So these values are coming from there. They were also provided, some of those were provided in that paper as well. So that's what I have used here. So this is start and for loading and unloading case. Then compression side, as you remember in that curve, reference temperature I'm using 0, but you can use whatever temperature was there. I think in that case they had 18.4, but I'm not doing any thermomechanical loading right now, so I'm just going to leave it like that. Then loading, this is again the change of stresses with respect to temperature. This is also given there, but at the moment it will not change anything because I'm not assigning any temperature values to that. Also, ABAQUS only uses a linear increase in temperature with respect to the linear increase in stresses with respect to temperature, and this is just 0 for this case because we are not having any shape setting effect. So again, all the data and everything is just, ABAQUS documentation is self-explanatory. Everything is explained here. You can look at that and you can definitely do everything what you really want to do. So this is the material properties I have defined. Then what you do is you create a section, you create a beam section. So what you do is you create a beam section here. In this case, I'm using a truss element, so I create a truss section. When I press continue, then I select this material properties and I press OK. You can also give the core cross section, whatever is there. And in this case, I have already defined, so I'm not going to create another one here. Then I assign this to this part, and I just do this, and then I assign it to this part. So this is how I have done here. And next is to assembly module. I can instance the part here, which I already have done it. So this is here, just click on this and then bring it here. Okay, so that's already there. Now I go to the step and I create a general step. So I have 3 steps here because in their case it was loading, then unloading, and then heating, and then again relaxing. So I'm just leaving it like that for the time being, but I will explain those once we reach to the next step where we have the matrix as well here. Okay, so this was just based on that. Just consider you have 1 step, right, for the timing. There is no interaction because it's just 1 component here, which is a fiber. So I leave it like that. Then I go to the loadings, and loading is very much the same as they had in their experiments. So I have no forces, but it was a displacement control test. So they had fixed because this is the one end of the matrix material, this is the other end of the matrix material. So I have fixed everything from one side, while on the other side I only let it move in the horizontal direction with the displacement of this, while I'm using an amplitude of amp1. And what is this amplitude? Again, you can create amplitude directly there, or you can create here from here. So you can create a amplitude button and you can give tabular, and then you can give the values here. So what I have defined here is at 0.0 it's 0, which is initial state. Then at half of the time step it will be 1, which is the maximum of the elongation, and then again it goes back to the 0. So I'm just trying to show you that my curve which was shown here can be somehow shown or predicted based on shape memory overlap properties of superelastic response in this case, because just trying to learn, this is the first step you always do. Rather than starting this complicated analysis, you first learn, okay, how do you model the shape memory overlaps, and how do you model the matrix material, how do you model the interface fracture in the matrix using node release technique, and then you combine everything together rather than start with the complex stuff. So everything is done incrementally. So this is what I have done here. So this goes like this and then comes back to 0 to capture that cyclic effect. Meshing, I only use one element here, so I just say the total length is 1. So if you see here, this is only 0.6, so well, I would say 6 the size, so I will have only one element here. Okay, and then I mesh it. So you can see I have only one truss element, and if I show you my truss element, so it is truss and it should be okay. Right, so that's what I have done here, but this was part 2. So part 2 is already meshed, which is basically the main part. Part 3 is the fictitious part I created just now. Alright, now I go to the job and I just submit the job, which is this one. Matrix, I will come back in the next video, so don't confuse with that. Submit, and it's one element, truss element, it's a linear element. You can even solve by hand if you have gone through my FEA course where I have showed you how to construct extension matrix for truss members. But why to do that if it's already there in the computer? Okay, so everything is going fine. You will see it finishes in quick time. My computer is getting slow because there are so many things going on right now. And then once it finishes, I go and results. So you can see, and this is step 1. So you see it starts to elongate and then it starts to contract back to the initial state. And that's what I have to plot, because step 2 and step 3 have nothing right now, because those are created for heating and cooling cycle, which I will explain in next video. Okay, now I go to the XY data manager, create field element label 1, save, and you will have the data now. And now you can combine them to get a stress strain response, because right now they are as a function of time, as you remember. So combine again, strains, then stresses, and then save, and I will just save it as a default name. Alright, so this is the data, and if I plot, so it looks like this. So you can see it has gone to that point, but it did never finish the whole transformation, so you just returned it back. So you have this loop, and that's why you have this thing. Alright, so we are able to capture. What you can do is, if you are not satisfied with the results, you can go back to the loading and you can basically increase the displacement to a larger value. Let's make it 0.5 now and see if I can finish the whole transformation thing and I can capture that cyclic effect which I want to see, right? So I'm just gonna go back to the job now, and then I will just submit again. It will not take more than 1 minute or so, so be patient, wait for it, and then you will get some fruit out of it. Right now I do this, and again I repeat the same exercise again for output post processing. I have created a lot of videos, so you can always find those videos to automate all this process which I'm repeating again and again. So create field output labels 1, save, create operate on XY data, combine, save. Now I'll save it as XY data 2, so let's go with that. Then I will plot, and so you see it goes like this, transformation occurs, then it comes back like this, and so it's following some trend which we are expecting, and you can further expand it and you can see it will completely finishes, but I will stick to this. So this way I am able to predict or simulate the pseudoelastic or superelastic response. The next step is to model the matrix elastic plastic response and how to model the crack propagation in it. That will be my next video, so please wait for that. And the third one will be combining these two together to have the final model. So I will see you in the next video. Thanks for watching, and you're always welcome to ask any questions, or if you have any problem which you want me to have a look, then definitely I'm more than happy to help. Bye for now and take care.